Greetings and welcome to Distillate. In the previous lecture, we talked about solving ordinary differential equations numerically. And we talked about a few explicit methods. We talked about the Euler's explicit method. So let's start with a tutorial on solving an ODE. Let's try to solve real world ordinary differential equations and real world initial value problems so that we are able to get a better understanding of the applications of ordinary differential equations in our field. So this tutorial deals with the evaluation of terminal velocity. The terminal velocity is just obtained by doing a force balance. But if we try to evaluate the evolution of velocity over time, we will see that at large times, the velocity goes to the terminal velocity. We'll talk about this in this lecture. So we'll first derive an expression for the ordinary differential equation that is used to evaluate the evolution of velocity. And then we'll also use that ordinary differential equation to evaluate an expression for terminal velocity, right? So we'll do these two things. And for that, we have to do a force balance. So let's start by understanding terminal velocity and all the interesting concepts associated with it. And then let's use Python to eventually solve the differential equation that we get from it, right? So for evaluating the expression or the ordinary differential equation that we need to solve for evaluating the terminal velocity, as I told you, we need to do a force balance. So let's define the system that we are dealing with. So we have, let's say, a fluid, and there is a particle that is falling inside this fluid, right? The density of the fluid is rho f, the density of the particle is rho p, the diameter of the particle is dp, it's falling down with the velocity v, right? That's the system that we are dealing with. And we are trying to understand how does its velocity, let's say if it starts at t equals to 0, let's say if it starts with the velocity v naught, what exactly or how exactly does its velocity profile evolve over time? That's what we are trying to evaluate using this system for this particular system, right? So let's perform a force balance on this particle. So if this is a particle of density rho p, and the diameter of the particle is dp, then in that case, the force that is acting on this particle is mass times the acceleration. So the mass is nothing but the density times the volume, which is nothing but pi dp cubed over 6. That's the mass that's the mass of the particle, right? Times acceleration, which is dv over dt, right? And that is equal to sum of all the forces that are acting on this particle, right? So now there are three major forces that are acting on this particle. The first very obvious force is the force of gravity, which is trying to pull the particle down. So that's nothing but rho p rho p times pi dp cubed over 6 times g, right? Then there is the buoyant force that is acting in the opposite direction, which is basically the fluid trying to push the particle out, right? And this is nothing but the weight of the fluid displaced by the particle itself. So the volume of the fluid displaced is equal to the volume of the particle. And hence the weight of the fluid displaced would be just rho f times the volume of the particle times g. This is the weight of the fluid that has been displaced, and this has to be subtracted because it's in the opposite direction. And finally, because there is relative motion between the particle and the fluid, there is going to be a frictional force, which in fluid mechanics we call as drag, right? So there's drag force that is acting. So that's minus Fd over here, right? Now, the other two forces, gravity and buoyancy, have a very nice expression for them. But the drag force is something that is not very trivial. So, to evaluate drag force, we actually define something called as the drag coefficient. Drag coefficient is nothing but a dimensionless drag force. Okay. So, if you talk about the force, let's try to see what exactly would be the dimensionless drag force. So if there is something, there's this particle that is flowing with the velocity v, or that is falling with the velocity v, right? So what could be the pressure, the uh, pressure difference acting around the particle? So the order of, or basically the order of magnitude of this pressure difference would go as half rho p v squared. This comes from the Bernoulli's equation, right? So considering this would be a good scale, good pressure scale to consider, right? Half rho p v squared. Uh, this actually comes from the Navier-Stokes directly, this scale for pressure. But let's just say that for now, we know, let's just assume that we know this pressure scale. And since the force is nothing but the area times pressure, so this is going to be half rho PV squared times the area. And when we are talking about the area, since the pressure acts in the normal direction and the drag force is acting in this direction, that means we are going to consider the pressure acting in this direction itself, right? So this eventually, the area over here, eventually what we consider is just the projected area of this particular sphere. So this actually becomes half, sorry, this goes as half rho p v squared times the projected area. So when a sphere is projected on a plane, it just becomes a circle. So that's pi dp squared over 4, right? So therefore, the non-dimensional or the dimensionless form of the force is just the drag force divided by half rho p v squared pi dp squared by 4. That is how we define the drag coefficient, right? That's how we define the drag coefficient. And from here, we are able to get the drag force as the drag coefficient times 1/8 rho p v squared by dp squared, right? That's how we get this drag force, right? Now, for Stokes flows, that is for Reynolds number less compared to 1, the drag coefficient is actually given as 24 over the Reynolds numbers. So the Reynolds number is nothing but rho Vd over mu. So this just becomes rho p v dp mu, right? And for turbulent flows, the drag coefficient becomes a constant 0.44, right? So in fact, this is how the drag coefficient varies with the Reynolds number. So something of this sort. So for low Reynolds numbers, we have it going as 1 over Re. For high Reynolds numbers, it goes as 0.44, right? So this is a very well documented curve. You will see this curve almost everywhere, wherever you try to evaluate drag coefficient versus Reynolds number. This curve is also available. This is the case for a spherical geometry, but it's also available for various other complex geometries. So this is a very well documented curve over here, right? So let's consider the Stokes flow case and consider the drag coefficient as this. And using that, we get the drag force as 3 times, okay, 3 times v by dp mu, right? Which is 3 by mu dpv. And this, you might have recognized this form of drag force is the Stokes law, or also known as Stokes drag, right? This is known as Stokes drag force or the Stokes law, right? So that's the drag force. So let's put this back into our differential equation over here, and we'll divide by this term. So we end up getting dv by dt is equal to g minus, okay, so this becomes g times rho p minus rho f by rho p. Let's just put that rho p minus rho f uh, divided by rho p, right? Minus the drag force, which is 3 pi mu dpv upon pi dp cubed over 6 times rho p, right? So maybe pi dp, yeah. So now let's just simplify this a little bit. So that is g rho p minus rho f over rho p minus, this becomes 18 mu v over rho p dp squared. That is dv over dt, right? And for terminal velocity, this is the differential equation. This is the ODE for velocity as a function of time, right? That's how you get it. And if you evaluate the terminal velocity, so when you evaluate terminal velocity, so there dv by dt becomes equal to 0, and therefore the terminal velocity becomes g times dp squared rho p minus rho f over 18 mu. That's how you evaluate the terminal velocity. So when we solve this ordinary differential equation, subjected to any initial condition, we must eventually retrieve the formula for terminal velocity at high times, at large enough times, right? So now that we have the differential equation, and remember, this is for Stokes flow. This is for Stokes flow, right? So now that we have the differential equation, let's go ahead and try to evaluate this numerically, right? So I have actually written some part of the code. Basically, I have imported the various um, libraries that might be required. I have considered the parameters, the acceleration due to gravity, the density of the particle, the density of the fluid, the diameter of the particle. This is in meters, which is 1 mm basically. And after that, we are going to solve this using the Euler's explicit method. So, or any method, any explicit method, if we are going to use, we'll need the initial condition and the initial array for velocity and time. This is the time step, which is 0.01 units of time. And we are going to consider till 100 seconds, and we'll see what happens after that, up to 100 seconds. And it should actually converge, or it should eventually go down to the terminal velocity by 100 seconds, right? So let's give it some initial velocity. Let's say that it is freely falling. So if it's freely falling, it would have an initial velocity of 0, right? Um, Now, then we have the code, the loop, basically for the Euler's explicit method. So over here, we are going to update the time array as well as the velocity array. So the time step is going to be just the previous time plus dt. That's what we are going to append for the next case. While the velocity case, so this is over here. So since we have dv by dt equals to this entire thing, which is nothing but some function of v comma t, not really of t, but since velocity is the function of t, we can say, but not necessarily. So it's just a function of velocity, right? So therefore, if we have to solve this using Euler's explicit method, we have to say vi plus 1 is equal to vi plus dt times f at vi, f evaluated at vi, right? Now this thing is just a constant, so we can just evaluate this. So maybe I'll evaluate the constant parameter over here. So that's g times rho p minus rho f upon rho p, and that's the constant parameter, right? So the next iteration is just going to be v at the previous iteration, which is vi plus, now over here, dt times the RHS of my ordinary differential equation evaluated at the previous iteration, right? So the RHS was constant, right? The constant value over here minus 18 mu upon rho p dp squared. So let's just write that down. So minus 18. I think I've not given the viscosity over here. The viscosity for air is about 10 to the power, I guess, minus 6. So that's 1 minus 5. I think that's the case. Yeah, it's 10 to the power minus 6. Yeah, so that's 1 minus 6, right? So 18 mu upon rho p dp squared 1 rho p times dp squared, right? And this times the velocity at the previous iteration, so v minus 1, right? That is the velocity. So this entire thing is the RHS of my ordinary differential equation evaluated at the previous iteration, multiplied by dt and added to the velocity at the previous iteration. That gives me the velocity, right? And now that we have the time as well as the velocity arrays, let's just evaluate. Let's just plot this. So plt dot plot t comma v, right? And the x label is time, y label is velocity. And let's just see what happens. So now as you see, this is where it is going. Let's maybe evaluate the terminal velocity. So the terminal velocity is g dp squared rho p minus rho f over 18 times mu. So the terminal velocity is actually 1361. So we probably have to go on for a long time. So let's go for, let's say, 10,000 time steps. So now you see, after a certain time, it has reached the terminal velocity. And if we see the last value of the velocity, that is just the terminal velocity, right? Closed, like it approaches the terminal velocity. So it has to asymptotically reach the terminal velocity, which is what we are getting over here. So we have been able to get to the terminal velocity using this ordinary differential equation, right? Now, you could also see how the various how various diameters would how the various parameters would affect the terminal settling. So for example, if instead of the fluid, in this case the fluid is air, but let's say if we replace the fluid by water, so let's just compare air and water. So the density of water is 1000, viscosity of water is 10 to the power minus 3. And maybe let's make another array VW, and we'll do the same thing. We'll evaluate the constant for water, which is just this. In place of rho f, it becomes rho fw, and we'll evaluate this thing. So VW over here. This is constant W. I'm just changing the differential equation over here, right? Mu water VW, right? Yeah, this is all that is there. And now let's add an additional thing for water. And to recognize them, we are going to make a legend plot. So we are going to label this as water, while this as air. So this is how you add legend. So basically you assign a label to each of the plots, and after that you just say plt.legend before you give the command for show. And if you see for both cases, actually it doesn't really show much for this long time. Maybe let's go for a shorter time. Let's see the terminal velocity for water. So it's actually very small. And if we evaluate that, so that's G dP squared times rho P minus rho water by, I think squared is double asterisk, over 18 times mu water. Okay, sorry. rho F water. Yeah, so that's 0.817499. So we are approaching the same terminal velocity. So as you see, the terminal velocity drastically changes when you use water in place of air, right? There's a drastic change. Let's use two similar fluids. So let's say we use oil, which has a density of 800. Sorry, that would be here. And the viscosity, let's just consider it to be the same, although there's a slight difference, but let's just consider it to be the same. And now if we see the terminal velocity, okay, this is not air, this is oil, but the terminal velocity for water is lower compared to that of oil because of the density difference for oil being larger compared to the density difference for water. So that means if we consider oil and what if we immerse particles in oil versus if we immerse particles in water, we'll see that particles sort of settle faster in oil compared to in water, right? That's one thing. Furthermore, we can do some other calculations, seeing, let's say, if we have a distribution of particles of various sizes. So let's say over here, we just consider one particle size of 1 mm. But let's say we have multiple particles from, let's say, 1 micron to 1 millimeter size. What exactly would be the velocity evolution of each of the particle? So we can do all of these calculations. I would not go ahead. I would not do this calculation maybe in this video, but in further videos, we could maybe enhance this code even further. I would highly recommend you to try this out yourself by considering, just like we've considered two different fluids, I would recommend you to try the same code, modify the same code for two different particles, for multiple particles, maybe see if you can generalize a code for, let's say, n particles and see how the velocity evolution takes place. If that seems very complicated, you could just see the differences between the terminal velocities for different particles and see where exactly is the terminal velocity going to lie for each of the particles, right? That could be a good exercise and a good practice in while you're dealing with Python. So this is a very interesting problem, and I really wanted to cover this because chemical engineers often come across this concept of terminal velocity and settling, because when you deal with problems related to sedimentation, um, this is a very important mechanical operation. You often are interested in the terminal velocity of a particle that you are trying to settle. And based on the terminal velocity and the time it requires to achieve that terminal velocity, leads to the fluid selection, the design of the sedimentation tank, how deep it needs to be, what should be the flow rate, and all of that is decided based on the calculations for terminal settling. So this is a very important concept that you must have come across in chemical engineering. So it's that's why I really want to cover this particular tutorial. In case there are other ordinary differential equations that you've come across in your chemical engineering curriculum and you would want me to talk more about those differential equations, please leave the comments. You could also ask for any doubts or anything in the comment section, or you could mail me. I've provided the mail ID in the description. And please just let me know if there's anything else that you need from these videos. Thank you so much.